Hey, what's up, guys? Yeah, so today I want to talk about uh, another fine local property called the noetherian, and I hope you guys subscribe to my channel. Yeah, so yeah, this is our goal. Okay, so we want to prove that this property is a fine local. So recall that a fine local basically is that if you have a skin and if if you have if for any affine first one is that if you have a spec A in X has property P, and we want to show that the spec AF, so each localization has property P. Okay, and the second one is that if A is generated by the ID, the idea is if A view ring as generated by the element F, then suppose each spec AF has property P. It won't show that the spec A has property P. Okay, so global to local, and if every local is true, then go to global. And I think previously I proved that the reduced and finitely generated algebra has the property. Generated algebra. Okay, so now let's go to noetherian. So this is also the Hawthorne proposition 3.2. I think it's chapter 3. So chapter 3, the first properties of skin. Yeah, if you are interested, you can check it. And I saw this is also in the Beckel. I think it's chapter 5. Okay. So the idea, yeah, so we need to first, so basically we need to show that the first one is that if A is noetherian, then AF is noetherian. And the second one is that we want to prove that if A is generated by this guy, and each AFI is noetherian. For every I, we want to show that A is noetherian. Oh, so first one is very simple. So we know we use the correspondence, right? So we know that the prime ideal is prime ideal, like not prime ideal, any ideal. So basically, let me just write down. So if you have A and S inverse A, there is a localization. So any ideal here, if this ideal is intersection with S is empty, then this ideal will map to S inverse I, then this guy will be the ideal of it. And any ideal J here must come from some another ideal. Let's call it J contraction. So this J contraction to the S inverse will become J. So basically the ideal is for this condition, the ideal of the ring N's localization is one-to-one correspondence. If you don't know how to prove it, you can check out my previous video. I have a video list. Okay, so noetherian means that right, so if things A so let's consider, right, so in AF, if I have the increasing chain, then this increasing chain will one-to-one corresponding to some ideal in A. And by a noetherian property that we know up to some points that all these will be the same. So this guy will terminate. Then the base one-to-one correspondence to the lower one will terminate. So this is the proof, right? Simple proof, very simple. Two is a little bit difficult. So before we prove it, let's work on with some simple lemma. Okay, so this lemma tell you that so lemma say that if you take ideal A, so this small a is ideal, and let's consider phi I to be a map into AF I. So this map is simple, just A map into A divided by 1 in the localization. Then we also lemma 6 say that A is the intersection of phi I inverse phi I A times AFI. Okay, so this time is a multiplication of ideal. So let me just quickly recall. If you take any two ideal ij, basically it's a summation of ij, where I belongs to I, j belongs to j. So this guy is ideal, this guy is also ideal, and you do the intersection. Okay, so this is our lemma. Let's quickly prove it. So you can see that this. So basically, this A is a subset of this intersection. This is simple because by definition, right, for fixed I, so for fixed I, you always have phi IA, the subset of phi IA AFI, because these guys one divided by one, right? So yeah, so any element, yeah, so this one is trivial, and so this guy, right, so A will be for each I, A will be a subset of phi inverse of it, so you can prove this. Okay, so another direction. So we want to do, let's say we take B. Let's say we take B belongs to A. And let's say B contained in the intersection. So we have this. Okay. Okay. So that means that this, right? So that means that for each phi B will be element of phi IA AFI. Okay, so that means that I can write phi B to be phi A times something, right? So numerator will be something A, let's call AI, and Fi to the Ni. And AI belongs to A, so A is ideal, and Ni is greater than 0. Okay, so this phi I map by definition is B divided by 1, right? B divided by 1. So in the localization property means that I can find Mi, right, such that Fi to the Mi, Fi Ni B minus A is 0. This is the definition of localization. So that means that I get okay. So that means that I get phi I Mi plus Ni B belongs to A, right? Because this A is ideal. Sorry, A is sorry, this is AI, right? So AI is the element in ideal, right? So this Fi Mi times AI, right, will be in A, will be in A. Hmm. Is this correct? Right. Yeah, because yeah, so AI is inside this ideal, right? So right, AI is in ideal. So any uh ring element RA will be in A. Okay. Yeah, so this is true. Okay, so that means right, this is so MI and NI are depend on I, right? Depend on I. Okay. Okay, so let's suppose, and we know that so suppose that F1, F2, let's say up to FR generated the whole ring A. Okay, so we can let's do this, right? So we can take, right? So for each I, there's Mi plus Ni, right? But I can take the least multiplier, so the least multiplier of this Mi plus Ni. So I can choose this Mi plus Ni to be large enough, right? To be large enough, such that every Mi plus Ni is the same. Okay, so that means I get I get a unique n who is large enough such that for every I, this fin will be times b will be in A. And as we prove the standard technique, if A is generated by this, then A is also generated by F1 to the N, F2 to the N, up to FR to the N. So that means that there is a coefficient HI, Fi to the N, I from 1 to N, I from 1 to R, such that this is A. So such that this is 1. This is 1. Okay, so I from 1 to R, HI, Fi to the N is 1. So that means that right, if you times B, then you get I from 1 to R, HI, Fi, N, B, which is B, right? So, but this proves that B belongs to A, right? Because now every these guys belongs to A, right? So, by the ideal is also subring, right? So B belongs to A. Okay, so B belongs to A, then we prove our results, right? Because we suppose that B belongs to this, and then B belongs to A. Okay, so now, yeah, let's neglect this. Sorry, this is the incorrect one. But it's fine. Okay. Okay, so now let's go to the proof, right? So let's prove the proof that our goal is to show that if F1 up to FR is A and FI is noetherian, then we want to say that the total A is noetherian. Okay, so proof, very simple, right? So suppose that we have an ideal A1, A2. Let's say it's the ascending chain in A. Okay, that means that that means what? That means that we always have phi I A1 times AF1 is the phi I A2 subset of AF2, sorry, AF1. And sorry, this is AFI. Sorry, I'm stupid. AFI. And the phi I A3 is AFI. Right? This is just by definition. So we have this. Now, if we take all the intersection, right? If we take all the intersection, okay. So this sorry. Notice that this guy is a ascending chain in this, right? So this is a ascending chain in AFI ideal. So this means that this for each I, right? For each I, that it will terminate. Okay, so you will terminate. Okay, but there's only finite I. So there must exist some larger enough number such that after that number that every small I ideal will terminate. And by definition, your A is there's an intersection lemma that we prove. So your this. Right, but after larger enough, n, then this guy will terminate. Will not change, so A will terminate. Okay, so that means the ascending chain will terminate due to the previous lemma. Yeah, I think this proof is beautiful because you use this interesting lemma that Harshon proof. Okay, so see you guys next videos. So this is our third affine local, and the next one we can talk about some definition. So very simple. See you guys next videos.